The Kepler Space Telescope monitors only one region of the night sky, in the constellations Cygnus and Lyra. Within this small area, the mission has already made an astounding number of detections, a total of nearly 5,000 candidates and confirmed planets. If the data shows anything, it's that our solar system, with its stable, nearly circular orbits, is a rare case. Most Sun-like stars are instead ringed with hot Jupiters and super-Earths that crowd their parent stars, leaving no room for planets like ours. The old theories about planetary formation are giving way to a new model, defined by fierce gravitational battles and titanic collisions. Scientists ask, what violent events shaped our solar system? And how did Earth manage to survive? What does the search for alien worlds tell us about the improbable rise of planet Earth? No doubt, our fascination with the night sky traces back to the dawn of our species. The movement of stars across the sky, the endless cycles of the moon and sun, the passage of seasons and years, defined the arc of our lives and inspired a sense of wonder. Inevitably, we began to search for principles to explain our observations and our own place within the universe. The first known astronomers lived in ancient Sumer in present-day Iraq about 4,000 years ago. They identified planets with gods and recorded their positions from season to season. In doing so, they were the first to divide a circle into 360 degrees and an hour into 60 minutes. The Babylonians took astronomy to a whole new level, using mathematics to track star positions. They identified constellations and developed precise calendars to predict the seasons. All the major ancient civilizations developed calendars, from Babylonians to the Chinese and Egyptians. But understanding seasonal cycles did not explain how it all fit together, or how we fit within the great firmament. Greek astronomers were the first to see the stars and planets as part of an ordered universe, a cosmos with Earth and humans at its center. The great philosopher Aristotle imagined a system of 55 concentric crystalline spheres that held the celestial objects. Each sphere would rotate independent of the others, with a unique velocity and direction. This idealized structure not only provided order to the universe, it defined the relationship between humans and the gods, who occupied the pristine outer spheres. The mathematician Pythagoras saw a fascinating pattern in the movements of planets. They embodied a series of mathematical ratios. Venus orbits 3 times for every one of Mars. Jupiter 5 times for Saturn's 2. These harmonies became known as the music of the spheres. But there were some disharmonies that needed explaining. Planets varied in brightness. Some appeared to switch direction, Still assuming that all revolves around Earth, the astronomer Claudius Ptolemy explained these puzzling patterns with an elaborate model of orbits within orbits. As Mars cycles through, it appears to go left from our point of view, then right. One astronomer, Aristarchus of Samos, saw the flaw in this model. He realized that Earth actually revolved around the Sun. This new assumption offered a simple explanation for Mars' apparent change in direction. Aristarchus faded into history, his ideas shot down by the well-respected Hipparchus, who felt obliged to defend the geocentric point of view. It took another 18 centuries for the heliocentric model to get another hearing at the dawn of the scientific revolution. By reintroducing it, the Polish scientist Nicholas Copernicus revitalized the push for a scientific explanation of planetary motions. Finally, in the 17th century, the laws of planetary motion were cemented by Johannes Kepler in his book Astronomia Nova. He published the book in 1609, the same year Galileo pioneered use of the telescope. By noting that the planets orbit in ellipses rather than perfect circles, Kepler showed how they can change speeds in the course of an orbit, or grow brighter by moving closer to Earth. Like Pythagoras so many centuries before, Kepler was fascinated by the lockstep relationship between some planetary orbits, what we now call resonances. To Kepler, these harmonies were evidence of the perfection of creation. They were the work of the ultimate master of geometry, God. Astronomers today, with their telescopes and algorithms, see these orbital patterns as a window into the early days of our solar system. Far from an ordered, perfect system, our solar system was formed in a violent and chaotic period that accompanied the birth of the Sun and led to the improbable emergence, you might say survival, of a planet we call Earth. It all begins about 5 billion years ago. Somewhere out in the galaxy is a dense and expansive cloud of dust and gas. At just above absolute zero in temperature, it's cold enough for molecules to form. The dense region within this cloud begins to slowly collapse in on itself. A slight spinning motion in the cloud causes the gas to flow in along a disk. As it reaches the center, the gas releases energy in the form of heat, forming a protostar with temperatures rising to several thousand degrees. High-speed jets begin to shoot out of its poles. After a few million years, thermonuclear fusion begins in the core. In the T-Tauri phase, the star has vigorous surface activity. Solar flares and eruptions account for their varying brightness. By linking an array of telescopes into one large observatory, a process known as interferometry, we can observe the star's irradiated disk. Once only a remnant of the star's formation, the disk begins to transform. This is TW Hydrae, a star 176 light-years away. Using ALMA, the Atacama Large Millimeter Array Telescope in Chile, astronomers have observed gaps within the disk. That's a sign that planets are beginning to form. Within the most prominent gap, 23 times the orbital distance of Earth, a planet 16% the size of Jupiter is taking shape. Another star, HL Tauri, already has multiple prominent gaps despite its young age, less than 100,000 years old. The standard explanation, the so-called accretion model, holds that planets grow slowly within such disks. Tiny particles of dust, some only a few molecules across, are pulled together by weak electrical attraction. The particles, now slightly larger, begin to bump into each other, growing into sand-like grains, then small rocks. The speed and chemical composition vary from rock to rock, causing some to combine, others to break apart. For those that do merge, their velocity increases, and so do the chances of shattering. Little by little, the rocks continue to grow in size. Soon, they have a gravitational field large enough to attract other rocks. If a so-called planetesimal becomes large enough and is located far enough from the Sun for water to turn to ice, it begins to accrete gas on top of its rocky core. This is the path to a Jupiter-like or Jovian planet. If a planetesimal is closer to the Sun, it may become a terrestrial planet, like Earth. Over millions of years, the theory says, the protoplanetary disk would evolve from a cloud of dust and gas to a collection of planetary bodies of all different sizes and classifications. But this theory fails to explain a few simple observations. How did giant Jupiter form on such a short time scale? How did Uranus and Neptune grow in the sparse outer regions of the disk? And why is there so little overall mass within the inner part of the solar system? Most of the mass of solar disks is packed into the inner region. And yet the combined mass of Mercury, Venus, Earth, and Mars is a little more than 0.5% the mass of Jupiter. Recent observations have led astronomers to adopt a whole new model of planetary formation and a radical new story of our solar system's birth. The ALMA Observatory captured the disk surrounding the star HD 142527. Astronomers looked closely at the differences in density from one end of the disk to the other. They concluded that as the disk spun around, spiral arms formed, like those that spin around a galaxy. These density waves have the effect of pushing some pockets of dust and gas out to the periphery. Out there, lower temperatures allow these clouds to rapidly condense to form a Jovian planet. This still doesn't account for the formation of terrestrial planets, or for the bizarre distribution of planets in other solar systems. Using the Kepler Space Telescope, astronomers have identified over 5,000 extrasolar planets. Some are unfamiliar, like the Chthonian planets. These extremely dense bodies are the remnant cores of gas giants that have had their atmospheres torn away by stellar winds. Then there is a class of large rocky worlds, super-Earths, up to 10 times the size of our planet. The majority are of a type foreign to our solar system, large gas planets that orbit close to their parent star. Some are packed so close to the star that their orbits take only days or months. These giants would have formed further out and migrated into the center, drawn by gravity. Scientists now believe that our solar system was not immune to such dramatic planetary movements. A new theory suggests that it happened over the course of about 600,000 years in a series of events they call the Grand Tack. The story begins during the early stages of solar evolution. A super-Earth could have formed near the core of the solar nebula. Soon after, the Sun came to life when nuclear fusion ignited in its core. Jupiter then formed at around 3.5 times the distance of Earth to the Sun, or just outside the asteroid belt today. Interactions with the solar disk would have caused the planet to lose angular momentum and to move inward to about the position of Mars. That threw the entire solar system out of balance. As it moved inward, Jupiter captured some of the rocks and planetesimals. It sent others into a flurry of shattering collisions. These collisions reduced much of the mass of the inner solar system to dust and small rocks, which then would have drifted down into the Sun. Our hypothetical super-Earth would have suffered a similar fate. If not destroyed by a series of unrelenting collisions, it would likely have been consumed by the Sun. Between the chaotic collisions and the destruction of the super-Earth, the inner solar system was left relatively free of rocks and gas. Then, something happened to Jupiter. It now began to move back toward the outer solar system. It was propelled by a type of gravitational interaction known as a mean motion resonance. When Saturn formed, it fell into an orbit with a ratio of 2 to 3 with Jupiter. The two planets tugged on each other and over time dragged each other farther and farther from the Sun. Meanwhile, with its remaining mass ground into minuscule fragments, the inner solar system was left with a clean slate. Terrestrial planet formation would begin again. The result, a whole new collection of small terrestrial planets. Mercury, Venus, Earth, and Mars. The power of the Grand Tack theory goes beyond the formation of these small rocky planets. In the standard understanding of solar system formation, terrestrial planets form early on. They not only grow large, but attract an excess of hydrogen, helium, carbon dioxide, methane, and other volatile compounds. These first-generation planets have highly dense atmospheres that are 1,000 times thicker than ours. Extreme surface temperatures make them uninhabitable. Earth, a second-generation planet, formed with a comparatively thin and shallow atmosphere, resistant to overheating, yet substantial enough to support moderate temperatures. With these initial conditions in place, Earth developed into a habitable world, home to over 8 million distinct species of plants and animals, and untold others that have come and gone over its long history. Pythagoras imagined that the workings of the universe could be described by a series of precise mathematical and physical functions. We now know that solar systems like ours are the result of countless events on scales ranging from the collision of particles of dust to the formation of a Jovian planet. Long ago, the accumulation of such events gave rise to our solar system. The havoc of a giant planet crashing toward the sun. The depletion of mass in the inner solar system. The formation of new generation terrestrial planets, including our own. As we scan the galaxy now for evidence of other worlds, we ask, is the story of Earth a common one, or is it wholly unique? For all we are learning about the universe, astronomy today is defined by ever deeper layers of unanswered questions. We forge onwards to decode the formulas and calculations of an evolving cosmos.